Okay, let's continue with this ENCOR lab. In this case, we are going to go for another topic. We are going to go now for 2.2.a VRFs and data virtualization paths. We are not going to cover all the data virtualization technologies, just some of them that belong to VRF LITE. So let's jump into the theory, and then we are going to go into the lab. VRFs stands for Virtual Routing and Forwarding. It is an extension of IP routing. This means that this is a layer 3 technology that provides multiple routing instances. So you can think of it as having one physical router, and in that physical router run several virtual routers. You can also think of it as VRFs are to routers what VLANs are to switches. So why do we need these VRFs at all? Remember, in all deployments, you could be able to separate traffic using VLANs at layer 2. However, when this very efficient separation of traffic reaches certain boundary, this traffic will land into the same bucket. Once this traffic reaches the layer 3 part of your network, all this traffic is actually being run as what we call as a global routing table. So in order to be able to separate this traffic at layer 3, you will use a lot of access control lists. Where this access control list, you will be able to set up roles like not permitting guest traffic to reach corporate traffic, and you could be able to separate your corporate traffic from your management traffic. So this was not really efficient at all. So the natural evolution is still having this natural separation of traffic at layer 2 with VLANs, but also being able to separate this traffic at layer 3. So with VRFs, you are able to make some traffic that belongs to some VLANs to land into a particular VRF, and some other traffic that belongs to another set of VLANs to land into a separate VRF. And you can also make the choice to make some traffic that belongs to some VLANs to land into the plain old vanilla routing table that we have been working with for years, that we are going to call the global routing table. So in this sense, you are able to actually separate traffic successfully at layer 2 and layer 3. So in summary, VRFs provide security by isolation at layer 3, pretty much as what we used to accomplish with VLANs at layer 2. So in this sense, you can, for instance, completely separate production traffic from management traffic, and you can separate guest traffic from corporate traffic, and so on. So each VRF will get its own separate set of resources. When you create a VRF, it will get automatically be assigned a RIV and a FIV. And then you can manually assign more resources to your VRF. You can assign sub-interfaces, physical interfaces, virtual interfaces like tunnels, and so on. By default, all the physical and virtual resources belong to the global routing table, but manually you can start assigning these resources to your VRFs. And also, VRFs are free to run its own routing protocols that will run independently from other VRFs. So these are, for instance, your commands to see your RIV for a particular VRF. This is the command to see your FIV for a particular VRF. In order to see how many interfaces each VRF has assigned, you can use this command. And in order to see how your routing protocols are behaving, you can always use this parameter VRF and the number and the name of your VRF in order to troubleshoot your routing protocols. Now that you have created successfully VRFs within your physical routers, the next question arises. How are you going to be able to communicate these VRFs that exist in different separate physical routers through a single link? For instance, in this case, we have two routers, router A and router B, and at each router you have created this red VRF, and you want this red VRF that lives in router A to communicate with this red VRF that lives in router B. So in order to do that, you have to virtualize your path. You have a physical path, and now you have to virtualize it. There are several virtualizing methods. We have these two, hop by hop and multi-hop, that are actually easy to understand but hard to configure. This provide a lot of work in order to get configured. And we have these other three methods that are somewhat harder to understand but are actually easier to configure. We are going to focus on these two methods here in this session because we are going to focus in something that is known as VRF LITE. Now, when using something that is known as VRF LITE, you can take advantage of encapsulation protocols in order to virtualize your path. And for instance, you can use these encapsulation protocols, AO2.1Q, GRE tunnels, frame relay, and the bottom line here for this idea is that VRF LITE uses virtual interfaces where each virtual interface belongs to each VRF. So, for instance, this is the basic idea behind VRF LITE and data path virtualization with VRF LITE. You are creating these VRFs here, VRF red, VRF green, VRF yellow, and we are going to consider these VRF LITE VRFs. Now, in this case, if you have three VRFs, you will need to create three virtual interfaces on each router. So in router A, you will have to create virtual interface number 1, virtual interface number 2, and virtual interface number 3, and the same applies for router B. Virtual interface number 1, virtual interface number 2, and virtual interface number 3. So this is how VRF LITE works with data path virtualization. So let's show some examples to put this in a more clear manner. So let's say that we are using three VRFs, red, green, and yellow, red, green, and yellow at each router. And in order to communicate these two sets of VRFs using one physical interface, we could go for instance, AO2.1Q. So with AO2.1Q, we will be able to create sub-interfaces, each one having a different VLAN, and then using this VLAN number, we could virtualize these physical interfaces into separate paths. So we will be achieving data path virtualization with the help of AO2.1Q. Notice that in order for this to work, if you had, for instance, 4 routers, router 1, router 2, router 3, and router 4, and if you had the same set of VRFs at each router and you wanted to communicate all these VRFs, you will have to do a lot of work, because even though you will only have one physical link connecting these routers, at each physical link you will have to create here 3 sub-interfaces, 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 and here 3 sub-interfaces. So that involves a lot of work. This is known as hop by hop data path virtualization, because you have to actually go and hop by hop configure these virtual interfaces, as many virtual interfaces as VRFs you want to communicate. Now, let's do an example of data path virtualization that is known as MULTIHOP. We are going to communicate these sets of VRFs between router A and router B. However, these routers are not connected back to back. They are connected through other routers, through a cloud of routers. So in this case, this technology that is known as GRE lets you do multi-hop data path virtualization, because it will let you communicate these VRFs through a series of intermediate routers. So we will be creating one tunnel here to communicate the red VRF, another tunnel here to communicate the green VRF, another tunnel here to communicate the yellow VRF. How are you going to be able to tell one router from the other using the key, the GRE key? Now, another example, if you are old enough, if you remember how to configure frame relay, remember that frame relay uses the DLCI numbers. These DLCI numbers are provided to you by your frame relay provider. So you could also be able to achieve data path virtualization with frame relay, because you can separate these PVCs using different DLCI numbers. Well, if you are old enough to know what frame relay is, you know this is an expensive. This was an expensive solution, because you actually had to pay your frame relay provider for each PVC that it is going to provide you. So, but it is still possible to be done with frame relay. So now the next question will be how well VRF LITE scales. So if you think about it, if you had 10 VRFs, you will need 10 virtual paths. And if you had 100 VRFs, you will require 100 virtual paths. And that is only talking about 2 routers. So therefore, VRF LITE does not scale well. The design best practice is, when using VRF LITE, keep the amount of VRFs low. For instance, less than 8. So with VRF LITE you can run, each VRF can run its own protocol. There are some routing protocols that are VRF aware, for instance, RIP version 2, IGRP, OSPF, BGP, and you can do static routing VRF. So you have several options here. You could choose to use a different routing protocol per VRF. So for instance, red VRF is running EIGRP, and this green VRF is running OSPF. This yellow VRF is running RIP, and this works, and this actually works. Or you can choose to use the same protocol. The red VRF is running EIGRP, the green VRF is running EIGRP, the yellow VRF is running EIGRP. However, these EIGRP protocols are running independent of each other. So you will have here an EIGRP topology table that will be completely different from this IGRP topology table, and these two will be completely different than this yellow EIGRP topology table. So each EIGRP will be running independent of whatever you are running in other VRFs. So how do you create a VRF? If you are looking at some old router config, you will see this. command in order to create a VRF. This command IPVRF and the VRF name was used in old iOSs. It has the disadvantage that it only supports IPv4. But if you are reading some recent iOS configurations, you will see this command, VRF definition and the VRF name. This new command is supported on recent iOS and iOS XEs, and it supports IPv4 and IPv6 address families. So this is old, and this is the new way of doing it. If you're configuring Nexus, you will use the command VRF context. Now, how do you assign interfaces or sub-interfaces or virtual interfaces or tunnel interfaces to your VRFs? The old way to do it will be going into the interface and executing this command, IPVRF forwarding and the VRF name. But the new way to do it is going into the interface, sub-interface, virtual interface, or whatever, and run this command, VRF forwarding. IPVRF forwarding is the old way. VRF forwarding is the new way. IPVRF forwarding is the old way. VRF forwarding is the new way. And if you're using Nexus, you would use VRF member. Now, remember that you can use address families for your VRFs. In this case, this means that you are enable this protocol for your VRF. So for the old configuration, you cannot use address families. But for the new configuration, you can actually go and type in address family IPv6. So you will be enable IPv6 or IPv4 for your VRF. For Nexus, you will use VRF member, address family IPv4, but Nexus requires you to use unicast or multicast as a parameter for. But just bear in mind that you have to enable, for instance, if you had an interface, let's say gigabit 00, and you only and let's say that you only configured in a VRF, let's say A, address family IPv4. And then if you wanted to enable IPv6, let's say that you want to assign this gigabit 00 to your VRF A, then you will issue VRF forwarding A, and then let's say that you wanted to enable IPv6 with the command IPv6 enable. In this case, this will yield an error because you have not yet enabled address family IPv6 within your VRF. So just be aware of enable your address families within your VRF before configuring IP addresses. Now, what happens if you come across a case where you have some old VRF configuration using the command IPVRF or IPVRF forwarding, and you want to upgrade that to the new style of configuration that uses VRF definition and VRF forwarding? You can use the command VRF upgrade CLI in order to do so. So in one single command, you can upgrade your configuration from the old way to configure VRFs into the new way. Now, let's talk a little bit about two concepts here that are known as the route distinguisher and the route table and route target. So in this case, something interesting happens if you mix VRF with BGP. You can do very interesting things when you mix VRF LITE with multi-protocol BGP. You can start doing some more complex and fun things with your VRFs. But before doing that, in order to start playing with this very good combination that is VRF LITE with multi-protocol BGP, you have to do two things. Configure something that is known as the route distinguisher and configure something that is known as the route target. So the route distinguisher identifies the router that is actually generating these prefixes or routes. So you will go into your VRF definition when you're creating your VRF definition and your VRF name, and then you will use this command for route distinguisher, and you will issue here a number, usually separated by a colon. So this will be your route distinguisher, and this will uniquely identify each router. That is the original purpose of the route distinguisher. So if you are careful when deploying route distinguishers across your network, you will be actually assigning an unique identifier for each router. So for instance, for this router number 1, your route distinguisher could be this. For this router number 2, your route distinguisher will be this. For router number 3, your route distinguisher will be this, and so on. So you have to be really careful, and you have to have a really good level of control in order to assign your route distinguishers for this. This is one way of doing it. Some network designers say, you know what, I don't really think that using the route distinguisher to identify each router is going to generate a lot of advantages for my network operation. So I just go and say route distinguisher, it will be equal to route target. So for all my red VRFs, I'm going to use the same route distinguisher. That will be the same as the route target. We are going to talk about route target in a second. But these are two ways of designing. I have seen these two ways configured in networks. Some network designers are really careful and have a lot of control of the assignment of route distinguishers and achieve this level of control where each router has a different route distinguisher. But other network designers say, you know what, I don't want to go into that hassle. It doesn't provide too much advantages, and I am going to use this rule. Route distinguishers is going to be equal to route target. And you can save a lot of human effort by taking that decision. Now, let's examine the other BGP thing or detail that we have to tune with VRFs. Remember that when combining VRF LITE and BGP, we have to do two configurations, route distinguisher and route target. We already talked about route distinguisher. Now let's talk about route target. Route target has two different configurations. The route target export and the route target import. So let's focus here and now in what is the route target export. With route target export, we are going to assign an identification for the prefix that come from a particular VRF. However, this ID is used only if these prefixes get imported into BGP using the redistribute or network command. So you can use route export in your configuration. You're free to do so. But if you are not using BGP and you are not injected into BGP your prefixes that belong to a certain VRF, your route target export configuration is meaningless. So remember that BGP has its own router, its own RIPs that are independent of your VRF RIPs. So if you want to actually inject VRF routing table into BGP, you have to use the redistribute or network command. But if you want also to assign these prefixes that you are going to inject into BGP with an ID, this is where the route target exports kick in. So by using route target export, you are going to tag, actually identify these prefixes that come from a particular VRF LITE into a BGP RIP. And BGP is going to internally use this route target export number as an extended community within its RIP in order to identify these prefixes. So for instance, these red VRF prefixes are configured with this route target export number, and if these prefixes are imported into BGP using the redistribute or network command, these prefixes will live inside BGP with this extended community 100. And for the green VRF that is configured with the 200 route target export, if these prefixes are imported into BGP using the redistribute or network command, they will be stored there within a particular RIP with the extended community 200. The same applied for the yellow VRF. So that is the only usage of the route target export feature. Now let's see the other half, which is the route target import feature. This feature will inject or import routes that have a certain route target number from a BGP RIP. It is really useful to do something that is known as route leaking. Remember that in order to do this magic, we require the help of a multi-protocol BGP. So, for instance, if you configure at your red VRF route target import 300, you are going to be able to import from BGP the prefixes that were previously admitted into BGP with the route target export with the same number. So notice here that with this little trick you can import or inject into your VRF prefixes that were previously sent into BGP by a different VRF. So that is one of the magics of the tricks, magic tricks that you can achieve when using the route target import feature. The other thing that the route target import feature is used for is this useful to express willingness at a certain router to receive prefixes coming from other routers when using multi-protocol BGP with BPMB4. We have not talked about this. Just bear in mind that if you don't actually use a route target import within your VRF, you are just going to drop all the prefixes that comes from other routers that happens to have this particular extended community. So that is why you will usually use route target export and route target import to the same number. But in this case, this is only meaningful when you have these types of neighborships with different routers using multi-protocol BGP VPN v4. So unless you're using multi-protocol BGP with VPN v4 or EVPN or something like that, it is really not useful to use route target import with the same number as the route target export. However, it is a best practice to use route target import and route target export to the same number. Now, you can configure several protocols. For instance, this is the way to configure RIP version 2 for VRFs. You can use OSPF version 2 with VRFs. Remember that OSPF version 2 will not support IPv6. And remember to use this little command to jump or not doing some certain routing checks that the protocol usually performs. If you want to work with VRF LITE, just issue this command, capability VRF LITE. You can also use OSPF version 3 with address families. In this case, you can use IPv4 and IPv6 address families with OSPF version 3. Remember to use the capability VRF LITE when using OSPF. You can use numbered EIGRP. Remember that numbered EIGRP does not support IPv6. Named EIGRP will support IPv6, so you can use address family IPv4 and address family IPv6. Just remember to enable your address families within your VRF definitions. Otherwise, you will not be able to use this address family with this VRF. Now, as a summary, we saw what VRF LITE is, what is data path virtualization. Remember that we saw several ways to perform data path virtualization, such as AO2.1Q, for instance, with GRE, with frame relay as well. We saw the old way to configure VRFs versus the new config. Remember that, for instance, all commands that starts with IP VRF or IP VRF forwarding are the old way to do it, and there is a new way to configure VRFs. We saw the way that we can use routing within VRFs. What are the VRF aware routing protocols, such as RIP version 2, OSPF version 3, version 2, and the difference between these. What are the VRF address families and how do you configure them? What are route distinguishers and route targets, and how to use route target export and route target import. These things work when combining VRF LITE plus multi-protocol BGP. Now let's go into the lab. Remember that in the lab we are going to be configuring VRFs here in this router, here in this layer 3 switch, here in this layer 3 switch, here in this router, and 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 this distribution switch, this distribution switch, this router, and this router. So we are going to be configuring there the global routing table for everything that has to do with the management of the network. And then we are going to set our VRFs. So we are going to create here a user VRF. User VRF. Here we will have a user VRF, user VRF, users VRF, users VRF, users VRF, users VRF, users VRF, users VRF, and users VRF. So we are going to use a users VRF for corporate users, and then we are going to use a different VRF for guest. So we are going to use the guest VRF, and we are going to set up here our guest VRF, guest VRF, guest VRF, and we're talking about VRF LITE. Now, this is how or where we're going to configure our VRFs, but we also need to do data path virtualization. So we will need to use a protocol in order to communicate these VRFs. So we're going to use here a particular .1q VLAN to communicate the guest VRFs between these two devices, another .1q VLAN to communicate these two devices, another .1q VLAN to communicate these two devices for VRF guest, and the same for all other communication. So in order to communicate the guest VRFs across devices, we are going to create these virtual data paths using different VLANs using .1q, and the same will apply for the user's VRF. So in order to communicate this VRF here with this other VRF here, we are going to use a particular AO2.1q VLAN in this link. The same for this, another AO2.1q VLAN in this link, a different AO2.1q VLAN in this link to communicate these two VRFs. The same for this one, and the same for this communication, and the same for this link. The same for this link between these two devices. The same for this link between these two devices. The same for this link. We are going to use AO2.1q VLANs in order to communicate these VRFs that exist in different devices. So we need data path virtualization. Notice the amount of work that we have to do in order to make this work. And in order to communicate the global routing table, we need to also use data path virtualization. So we will need another VLAN using AO2.1q to communicate these two global routing tables. So notice the amount of work that you have to do when using VRF LITE. This is the amount of VLANs that you have to configure in your routers in order to make all of this work. Now, we will also need GRE tunnels to communicate our VRFs. So in order to communicate the user's VRF that exists in this blue network with the user's VRF that exists in this green network, we are going to set up GRE tunnels. And the same applies for the user for the guest VRF. However, not really needed, because the guest VRF only needs to reach the internet in order to work, so we don't really need to communicate the guest VRF. However, we will need to create tunnels in order to communicate the global routing table between these two different separate networks. So this is the amount of links and AO2.1q VLANs that you have to use when using only 2 VRFs. If you were using 5 VRFs or 10 VRFs, the amount of configuration here that you will need will be a lot more cumbersome. It will involve more effort. So let's see how the lab is configured in order to achieve this inter-VRF communication using data path virtualization. So let's jump into the lab. So let's, for instance, see how router A1 in the green and the blue network is configured. So let's see what VRFs do I have with show IP VRF. So we have the guest VRF that has these interfaces, the users VRF that has these interfaces, and we are working with switch 4 here. I'm sorry, in router 1 we'll have these interfaces for the guest VRF. For instance, gigabit 20.12.02 is the virtualized data path that connects router A1 to router A2, and gigabit 30.13.02 is the virtualized data path that connects the guest VRFs between router A1 and switch 3, and gigabit 40.14.02 will be the virtualized data path that connects router A1 with switch 4. In the same manner, for users, gigabit 20.12.01 is the virtualized data path that connects the user's VRFs between router A1 and router A2. This interface will be the virtualized data path that connects the user's VRF between router A1 and switch 3. This will be for connecting the user's VRF between router A1 and switch 4, and this will be the connection between router A1 and router C1 for the user's VRF. So notice the amount of configuration that has to be entered in order to do virtual path configuration. The same applies for router A2, and the same for the switches, my distribution switches. In this case, we're using SBIs to communicate or to build this virtualized data path. So, for instance, virtual VLAN, let's say 301, 1301, I'm sorry. Exists only in gigabit 01, which is the interface that connects switch 3 with router A1. So, and if we wanted to see how it is configured, we'll see that it is attached to VRF users. 1302 is for guest, and 1300 will be for management. The same applies for the routers. So just notice the amount of configuration you have to execute. So let's go, for instance, here for the green network. Show IP VRF. Notice that you can also run your routing table by VRF. So show IP route VRF users. that is different from the global routing table. So this is the global routing table. This is the users routing table. This is the guest routing table. The same way you have your fib, show IPsef, for the global routing table. Your fib for your users VRF, and your fib for your guest VRF. Now let's see how it is configured. For instance, let's see how the VRFs are created. So we have the guest with IPv4. We have users with IPv4 and IPv6. So this is how we actually configure the VRFs. And in order to assign an interface to a VRF, for instance, this interface, we match the VRF with, we actually apply a VRF name to the interface, and then, for instance, after doing so, this interface now it's listed to be part of the VRF that it was configured with. So remember the commands to check your VRF, show IP VRF, to see how many VRFs and what interfaces you have. You can issue show IP VRF users to see particularly what is your the interfaces that belong to this particular VRF. Remember that we can configure a route distinguisher. In this case, no route distinguisher is configured yet, so we can go and do VRF definition users and then configure route distinguisher, for instance 1, and then it will show up here. We also have a VRF for the internet, because these links that go to the router internet one belong to another VRF, that is the internet VRF. So if we issue show run interface gigabit 60, we'll see that this interface that connects to the internet has this command. We can also issue show IPv6 route per VRF. So we have not yet configured here routing protocols. So that will be the next step. We are just doing a lab for configuring and verifying VRFs. So how do you configure your VRFs? Using the command VRF definition, and establish inside the VRF definition your address families, and then bind your interfaces into your VRFs. So for instance, this using VRF forwarding, Now for Nexus, the commands are a little bit different, but the idea is practically the same. So, for instance, to create VRFs, you will use the command VRF context and your address family. And then to assign a particular interface to your VRF, you will use VRF member. Compare that with iOS, where you use VRF definition and VRF forwarding. With Nexus, the commands are VRF context and VRF member. Okay, the commands are different, but that will be how to configure and verify data path virtualization with these commands. Show IP VRF. This is how we are achieving data path virtualization. And that's it. The next lab will be actually configuring routing protocols for each VRF.